In this video, we will go over how to use Microsoft Excel to calculate the statistical analyses that you will need for the remainder of the semester, including standard deviation, standard error, and t-tests to calculate p-values. I will be using Microsoft Excel in this tutorial, Microsoft Excel desktop application that can be downloaded for free through your Office 365 Illinois State subscription. I do not recommend using the online application of Microsoft Excel or the Google equivalent, as the functionalities are a little bit different. If you have any questions about how to download the Microsoft Excel desktop application from Office 365, please contact the head TA as soon as possible so that we can get you running with this program. Okay, for an example today, we will be using two data sets. A control data set that was measured, that measured plant growth in control soil, and experimental samples which measured plant growth in experimental soil. We have collected 5 individual data points from each data set. To calculate the average, we will need to use an Excel equation. All Excel equations will begin with an equal sign. The Excel equation to calculate average is equals average, open parentheses, select all the data you wish to average, end parentheses. We can do the same with the experimental samples. Equals average. Next, we want to calculate the standard deviation of our samples. This can be done with the equation equals STDEV. You'll notice there are several ways to calculate standard deviations with different qualifiers. However, in this course, we want to use just simple standard deviation with no qualifiers. STDEV, open parentheses, then select all the data in your data set. You want to make sure you do not select your average because this is not one of our original 5 data points. End parentheses, enter. We can do the same with our experimental samples. Equals STDEV, open parentheses, select all data, enter. To calculate standard error in Excel, there is no preset formula. However, we do know the equation to calculate standard error is the standard deviation divided by the square root of n, where n is the number of samples in your data set. In both our control and experimental data sets, our n is 5. So to calculate our standard error for our control, we will hit equals, select our standard deviation cell. By clicking on this cell, it will move this value into this position. Oops. This one. Divided by, which is the backslash, the square root of 5. To calculate square root, it is SQRT, parentheses, 5, end parentheses, enter. This will calculate our standard error. We can do the same for our experimental sample. Equals our standard deviation divided by the square root of 5. We have now calculated the average, standard deviation, and standard error of these two data sets. We can next calculate our t-value between these two data sets to determine if they are significantly different. To do so, we will use the equation outlined here. To perform this equation, we need the average of our experimental sample, which we have already calculated here, the average of our control sample, which we've already calculated here, the standard error squared of our experimental sample, and the standard error squared of our control sample. To calculate our denominator and our numerator, I like to move them into more organized columns. So to move our standard error control from our control equals our standard error that we calculated previously. We can do the same with our experimental value. This column will equal the standard error of our experimental. Next, we want to take the square of this value. To do this, equals our standard error, caret sign, 2, which is the Excel formula for squaring. We can do the same with our experimental sample. Equals our standard error squared. To solve for our denominator, we next need to take the sum of these two values. To do this, equals standard error squared control plus standard error experimental. We next need to take the square root of this value, which will give us our final denominator value. Again, equals square root of the sum of standard error squared. This will give us our denominator value. To calculate our numerator value, simply equals experimental average minus control average. Enter. We can now plug these two values in to calculate our t-value. Equals our numerator divided by our denominator to give us a t-value of 4.5607. We next need to calculate our degrees of freedom, which is calculated by the equation n of experimental plus n of control minus 2. So recall, we've already determined that the n for both control and experimental samples equals 5. So degrees of freedom will equal 5 plus 5, this value minus 2, giving us a degrees of freedom of 8 with a t-value 4.56. We can next use the t-value chart to determine our p-value. That looks something like this, where on this axis, our degrees of freedom are shown. We calculated our degrees of freedom to be 8. We will then go across the row at the degrees of freedom 8 point to find where our calculated t-value, which was 4.56, where that will fall between our critical t-values. So 4.56 is larger than 1.397. It is larger than 1.86. It is larger than 2.305. It is larger than 2.805. It is larger than 3.35, but it is not larger than 5.041. So our calculated t-value lies between these two columns at this point. We can then go to the top of the column where our p-values are located. So going to the top of the column, this shows that our p-value is between 0.001 and 0.01. This could be represented as p is greater than 0.001 but less than 0.01. Your p-value will always be a range and not an exact number. To report this value, you may simply say p is less than 0.01. Because this p-value is less than 0.05, which is our cutoff point for determining whether two sets of data are significantly different, with 0.01 being less than 0.05, we can determine that our two data sets, our control and experimental data sets, are significantly different. This concludes the Microsoft Excel tutorial for BSC 197.